Now we will move on to the 1.4 periodic relationship in the compounds. A. Halides. Halides are the binary compounds which halogen form with other elements. The physical properties of halides are largely determined by the nature of bonding present in them. On the basis, halides can be classified in two general classes, ionic and covalent. In between the two, there is another class of halides in which the halogen atom acts as bridge between the two atoms of the other element. Such halides are termed as polymeric halides. Strongly electropositive elements having greater electronegativity difference with halogen atom form ionic halides. The halides of group 1A are considered purely ionic, which are high melting point solids. Such halides have three-dimensional lattices consisting of discrete ions. Melting point of chloride of period 3 elements and their bonding character is shown in this table. NaCl, its melting point is 808 and the type of bonding is ionic. Magnesium chloride 715 melting point and partially ionic. Aluminum tetrachloride 192 melting point and type of bonding is partially ionic. Silicon tetrachloride is minus 68 degrees Celsius and type of bonding is partially covalent. Phosphorus trichloride is minus 93 and partially covalent, and sulfur disulfur chloride is minus 80 partially covalent as well. Among the pure ionic compounds, the fluorides have the highest lattice energies due to the small size of fluoride ion. Thus, for ionic halides, the fluorides have the highest melting and boiling points, which decrease in order: fluoride, chloride, bromide, iodide. Less electropositive elements such as beryllium, gallium, and aluminium form polymeric halides having partially ionic bonding with layer of chain lattices. The lattice of silicon tetrachloride consists of discrete molecules which are highly polar. The bonds in the PCl3 and S2Cl2 are less polar than those of SiCl4. On moving across the periodic table from left to right, the electronegativity difference reduces and the trend shifts towards covalent halides. The gradual change in bond type and melting points of the chlorides on moving across the period 3 of the periodic table is shown in the table 1.3. As the intermolecular forces in covalent halide molecules are weak van der Waals forces, so they are often gases, liquids, or low melting point solids. Physical properties of covalent halides are influenced by the size and polarizability of the halogen atom. Iodides, as being the largest and the most polarizable ions, possess the strongest van der Waals forces and therefore have higher melting and boiling points than those of the covalent halides. The variation in the bonding character is also present in descending from top to bottom in the halogen group. In general, for a metal, the order of decreasing ionic character of the halide is fluoride, chloride, bromide, and iodide. For example, aluminum fluoride is purely ionic compound having melting point 1290 degrees Celsius and fairly a good conductor, whereas Al(I3) is predominantly covalent with melting point 198 degrees Celsius and is electrically a non-conductor. In case of an element forming more than one halides, the metal halide in its lower oxidation states tends to be ionic, while that in the higher oxidation state is covalent. For example, PbCl2 is mainly ionic and PbCl4 is fairly covalent. This can again be explained by the high polarizing power of Pb4 plus as compared to Pb2 plus. Part B is hydrides. The binary compounds of hydrogen with other atoms are called hydrides. According to the nature of the bonding, hydrides may be broadly classified into three classes: ionic, covalent, and intermediate. The elements of group 1A and the heavier members of the group 2A form ionic hydrides, which contain H- hydride ion. These hydrides are crystalline solid compounds with high melting and boiling points and which conduct electricity in molten state. The tendency toward covalent character increases by moving from left to right in the periodic table. Hydrides of beryllium and magnesium represent the class of intermediate hydrides. Their properties are in between the ionic and covalent hydrides. They have polymeric structure and covalent nature. Table 1.4 shows hydrides of the elements of 1A, 2, 7A and 2B subgroups. The division is shown ionic, intermediate and covalent among the 8 groups. The covalent hydrides are usually gases or volatile liquids. They are non-conductors and dissolve in organic solvents. Their bond energies depend on the size and the electronegativity of the element. Stability of covalent hydrides increases from left to right in a period and decreases from top to bottom in a group. Fluorine forms the most stable hydride and the least stable are those of thallium, lead and bismuth. These hydrides are formed by elements with electronegativity values greater than 1.8, which we call the Pauling scale. Since the electronegativity of hydrogen is 2.1, most of these hydrides have polar covalent bonds in which hydrogen is carrying a slight positive charge. On moving from left to right across a period, the electronegativity of the other element increases and the hydrogen element bond becomes more polar. Due to high polarity, the hydrides like H2O and HF are capable of forming hydrogen bonds between their molecules. The boiling points of covalent hydrides generally increase on descending a group as shown in table 1.5, except the hydrides like H2O, HF and NH3 which due to hydrogen bonding have higher boiling points than might be expected. The table 1.5 shows melting and boiling points of hydrides of group 4A and 6A. As you can show the hydrides and their properties, their melting and boiling point. Numbers Charlie is oxides. Oxygen forms compounds called oxides. With almost every other element in the periodic table, since many of these have quite unusual properties, there is a extensive and varied chemistry on the compounds of oxygen. Oxides can be classified in more than one ways based upon the type of bonding they have as well as their acidic or basic character. We shall discuss here the classification based on their acidic or basic behavior. This chapter you have already studied that metal oxides are basic in character as they yield bases in water and non-metallic oxides are acidic because they form acids in water. Basic oxides and acidic oxides react with one another to give salts. For example, Na2O plus SO3 is Na2SO4. There is a third type of oxide which shows both acidic and basic properties, and these oxides are we call them amphoteric oxides. The classification of elements which form oxides of acidic or basic properties is shown in table 1.6, in which the basic, amphoteric and acidic oxide making elements are shown. The oxides of alkali and alkaline earth metals except beryllium are basic and contain O2- ion. The O2- ion has a high affinity for proton and cannot exist alone in aqueous solution. Therefore, it immediately takes proton from water and forms OH negative ion. Oxides of non-metallic elements like the carbon, nitrogen and phosphorus and sulfur are acidic in nature. They generally dissolve in water to produce acidic solutions. Oxide of relatively less electropositive elements such as the beryllium oxide, aluminium trioxide, and Bi2O3 and zinc ZNO are amphoteric and behave as acid towards strong bases and as bases towards strong acids. ZNO plus H2SO4 gives us ZnSO4 plus H2O. ZNO plus 2NO NaOH plus H2O gives us Na2ZnOH4, which is in the aqueous form as well. In a given period, the oxides progress from strongly basic through weakly basic, amphoteric, and weakly acidic to strongly acidic. Example Na2O, MgO, Al2O3, P4O10, SO3, Cl2O7. The basicity of main group metal oxide increases on descending a group of the periodic table. Beryllium oxide, magnesium oxide, calcium oxide, strontium oxide, barium oxide. Through the reverse trend is observed in the transition metal oxides. The oxidation states of the metal also affects the acid-base character of its oxide. The acidity increases with increasing oxidation state. The acidity of MnO, Mn2O3, MnO2, and Mn2O7 can be used to show the increasing oxidation state. Allah Hafiz.